Hi, this is ET250 Lecture 9. Today we're going to talk about strain gauges. Strain gauges are these little sensors that are just a bunch of long wires, and they change their resistance when you stretch and strain material. We'll talk about their equation, and then we'll look at a Wheatstone bridge configuration, which will include four resistors. This is the condition of those resistors when they're balanced. We'll look at how to measure small changes in R, because essentially the strain gauge is a big resistor, right? It's a wire, and the wire has resistance, and it changes just a small amount when you know stretch and compress these things. So we'll look at how do we measure that R, and then we'll put it all together and go over this example of a bicycle pedal power meter. And so we'll see how can we combine a unique configuration of strain gauges, how can we use this Wheatstone bridge idea, and how can we even pull up some of these mechanical concepts like stress and strain and force. And so maybe in your material science classes and strength of materials, you can see a familiar equation here, right? And then related to mechanical power, like if you're literally on a bicycle pedaling, how could you measure the power of one of the pedals? And so we can look at this equation, which we'll show, is basically related to all these. And the idea is using a voltmeter and a speed sensor, you can actually calculate the power, right? And then this is just the material constants and geometry of your system, but they could all be just lumped into one constant. So the idea is, how could you take a strain sensor, which you can read from a voltage, and then a speed sensor, which with maybe a gyroscope, and then get power. So yeah, let's begin. So again, if we look at this, this is a strain gauge, and it's mounted. It's like really nicely adhered to this piece of metal. And if a force was being applied to this metal would stress and strain, and so would this little patch with these wires. Okay, and so I have the same thing drawn here. And this is definitely useful for measuring forces and pressures because, as we know from our strength of materials, stress and strain and forces are all proportional to each other, right? If you look closely, you can see that the wires are oriented in this fashion, right? Along this axis. Okay, so that's important because if I pull in this direction, you can see that this wire stretches, right? And so you're going to get a change in resistance with that change in length. However, if I were to pull in this direction, it's insensitive because, yeah, you get a little bit of stretching here, but not very much. So it's insensitive to this axis and sensitive to this one. So that's something important to note. Okay, recall from our earlier discussions on resistance, R equals rho L over A. And so the length of this wire is what affects this resistance if it were to stretch, right? And so we can say if we have a delta L, we're gonna get a delta R, right? Okay, let's keep going. So this is the equation that relates the change in resistance to the strain of this wire, right? And so what do we have here? Strain, right? What is strain? Change in L and over L equals 1 over this factor, this gauge factor, which is the number 2, and you'll actually show that in the homework, times the change in resistance divided by the nominal unstrained resistance, right? So the nominal unstrained resistance is just what is just the nominal resistance of this wire without any stress on it. No strain, no stress, okay? Okay, and so the idea is if we can measure change in R, right, we can measure or we can estimate what the actual strain is, the change in L over L is. And we can measure the change in R using a Wheatstone bridge and a voltmeter, right? Because, and then here's the point, because change in R is very, very small, I can't just put an ohm meter to it and measure it. It's just not sensitive enough. You need some special circuitry. Okay, so what's a special circuitry that would help us measure this very small change in R? Well, we could use this thing called a Wheatstone bridge circuit, right? So you have a nice constant fixed voltage supply. And look at these resistors, 1, 2, 3, and 4. So there's 4 resistors in this bridge-like configuration. And what I'm doing is I'm putting a very sensitive voltmeter here, and we might have to amplify this voltage, right? So sorry, red lead, black lead. So we're going to be putting a sensitive voltmeter here, and it's not just any voltmeter. It is like an amplified signal, so read by probably a microcontroller, but let's just write voltmeter for now, right? Now imagine these are known, and this R3 is an adjustable, like a rheostat potentiometer kind of thing, where you can adjust this resistance, okay? And you can easily adjust it, and then you have your strain gauge. Well, what is these? I mean, we drew a resistor. I thought it was just a wire. It is just a wire. These two terminals here would be these two terminals there, okay? And so when this is what we call balanced, remember, this is just a voltmeter here. When this is balanced, the voltage, the node voltage at A minus the node voltage at B is going to be 0. That's what we call the balance condition, right? And for this to be true, the product of these diagonals have to be equal. So R1 R gauge equals R2 R3. And you can kind of think of it, we'll show why, but you can kind of think of it as like a balanced voltage divider, right? So if it's in the balanced condition, we know what R gauge is based on the other three values, right? You can solve for this one equation, one unknown, right? Okay, so keep that in mind. Now, if you want to prove why it's balanced, we can look at it real quick. It's not that bad. Here's the voltage divider relation. Remember, the node voltage VA is technically the voltage from here to the ground. Okay, so that's the voltage over R3. So the voltage divider, look, these are in series. Assume no current goes through here. This is a voltmeter, right? Very little current, negligible current goes through here. So these two are in series, and we have VA is equal to R3 over R1 over R1 plus R3 times VS. That's what we have here, okay? And we have VB equals R gauge over R2 plus R gauge, right? That's what we have here, okay? And the difference, VA minus VB, is 0, right? Because that's their balance condition. Okay? So we can take these two and subtract them and set them equal to 0, which we have. Notice the VS cancels, and I get this, right? And if I solve this, crunch, 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 or just reduce it, I should say, I should get that, right? So I can bring one of these to the other side, which I have. I can cross multiply the denominator, right? So this R2, R3 goes up to there, and this R1, R3 goes up to there. Good. And I notice that I get a cancellation when I distribute these guys in, and I'm just left with this and this. Okay, so it's not too bad to see that when it's balanced, right? That's why we have that condition here. We get this nice relationship, and that's why this is true. Okay, but don't get lost in detail. The idea here is we are trying to measure that R gauge, very small changes in resistance. Okay, so how would we measure this change in resistance here? Remember, don't get lost. We have this equation, we have this Wheatstone bridge, and we have this physical setup here, right? So this is R gauge, that's this guy. All right. So the first step is, let's say we have this R3, right? And we can adjust R3, and we can be reading this voltmeter. And what we can do is we can go, okay, let's say there's no strain on it. I haven't stretched this at all. It's in this resting condition. And I can tune this R3, right? Let's say the R3 is actually a big number. And we can tune it until we see 0 volts across here. Now, let's say R3 you could read with an ohm meter, right? So let's say R1, R2, and R3 are now known. So these are big values which you can read off of ohm meter. Then our gauge, we could now know that perfectly using our balanced condition, right? Because this is only valid when this is 0, okay? So that's the first thing you could do. Then what you could do is you could apply your force, stretch it out. So we're in the laboratory, you apply your force, okay? And then what you need to do, or what we realize is that we know that there's going to be a new R gauge value, right? Because if you, let's say, stretch it, the length is going to increase, the resistance is going to increase. So we're going to get a new value for, we'll call it R gauge prime, okay? And what? Now we got to rebalance the bridge, adjust R3, right? Get this to 0, use our nice balanced relationship here, and then solve for the new R gauge prime, okay? We know what this R naught was originally. That's when the unstrained case, right? And so then we can subtract that off. We can get this delta R, right? And we get delta R equals the new version minus the original. Okay, that delta R goes into this equation here and we get the strain. My goodness, what a painful process, right? So just to recap, balance, apply force, balance again. Seems like it's very prone to error, but that is one process to get the strain measurements out of here. Wouldn't it be nicer if there was a faster, more reliable process, right? And so I highlight that here. Slow and tedious process. The single strain gauge is a problem. It doesn't handle temperature fluctuations well. It may confuse forces from different directions, even though it only, it has one, it does only have one sensitive force, but you'll see why a single strain gauge could be a problem. And so a solution is to use a full Wheatstone bridge. So we're still using a Wheatstone bridge, but we're going to put a gauge. We're going to use 4 gauges. We're going to use a gauge for every single one of these. And we'll see why this new version or this new configuration is even better than what we just showed. Okay. All right. So let's look at this bicycle pedal power meter. And I'm hoping this example kind of puts everything together. Okay. How we can use multiple strain gauges and how we can be insensitive to different forces, and just puts it all together in a nice package, nice application. All right. So remember, tedious process, slow with 1 gauge. We're going to use 4 in this example. Now, let's say we have a bicycle, okay? And we want to measure the power of 1 pedal. And we know mechanical power is torque times angular velocity, or it's force times distance, pedal length times angular velocity, okay? So that's just the definition of torque, okay? No problem with there. So this equation we keep in our mind, okay? Now, how could you measure this? You could use a cadence meter, just like on your bike. You can get the angular velocity from the cadence meter. How do you get this number? Well, this number you can get from just literally measuring where your foot is pressing on the pedal, okay? What about this one, force of the pedaler? Well, this is where we're going to get it from the strain gauge, right? And the strain gauge is going to come from a voltmeter. You'll see how we get that in the rest of this discussion. Okay, so what does the picture look like? I have my pedal, right? I have the pivot point to the pivot point. That's my LP. I have omega. This is the rate at spin, and I have some force being applied. Okay, great. So let's model this as a beam. I know it's not exactly what's going on, but maybe this is a good way to simplify things, just so that we can get a handle on the dynamics of the system. So imagine I have a beam, I have LP, I have force P, and we want to put a strain gauge on that pedal, because if we put a strain gauge on that pedal, we can measure what that force is, right? Okay, good. So remember the first example, 1 strain gauge, okay? Now you can imagine if you had a force here pushing down, sometimes you don't always push it perfectly perpendicular to the pedal. You don't always push it down. Sometimes you have a little bit of horizontal component, right? The problem with that is this strain gauge cannot tell the difference between this orientation of force or this orientation of force. Can you imagine if I push down on the top, you get tension on the top here, right? If I were to pull with FH, can you imagine you also get tension on here? Okay, so you can see how this strain gauge, the single one, would get confused. It would not know the difference between this and this. This one would be contributing to your power, and this one wouldn't. This would just be pushing into the pivot, right? So maybe there's a configuration where we can ignore this one and get this one. Okay. All right, basically what I said is just what I wrote down here. Okay, so here's the solution. Instead of using 1 strain gauge, you use 4. And like I said, in this full Wheatstone bridge configuration. And what we're going to do is we would put 2 on the top and 2 on the bottom, right? So you have 2 on the top, 2 on the bottom. We have force going down from your pedal and force going horizontally. They could be simultaneous because your foot could be pushing at any angle here. But like I said, we want to just account for this one. All right. So force, let's imagine what happens if we had force on the pedal. And let's say this goes up. Okay. So if this goes up in force, not like up in direction, but let's say this is applying a force harder and harder and harder. Okay, what's going to happen? The top 2, so we'll call these the RTs. They're all exactly the same strain gauge. The RTs, they are going to be in tension, so they're going to stretch. So you're going to get a delta R positive. But on the bottom two, the RBs are going to get a delta R but negative. So they get opposite in terms of their change from a perpendicular force. Okay. The horizontal component, let's say this horizontal component increased, right? Okay. So if this increased, you're going to compress all four of these. So they're all going to get smaller. So they're all going to get a delta R negative, right? Yep. Good. Okay, so let's review that. Perpendicular force will get opposite delta R's, whereas a horizontal force will get the same delta R's, right? Even if I stretch it out, it'll be positive delta R's on all of these. Even if I pull it up, it'll be positive delta R, negative delta R, because these will be in tension compression if I pull this force up. Okay, good. Okay, so then this is the configuration. Like I said, you're going to put them opposite of each other in the Wheatstone bridge. Again, you still have that voltmeter, very sensitive voltmeter. Assume no current goes through there, right? But it's still the same setup as before, but no potentiometer or anything, right? And we're going to see how we can, on the fly, not having to do this whole balance silliness, but on the fly, get the strain or delta R and then the strain of the entire thing, which will relate to the force FP, and we can find the power. Okay. Okay. So that's exactly what I said. Use the voltmeter, get the delta R, get the strain, get the force, get the power. Yes. Okay. And we don't want to be sensitive to FH, only sensitive to FP, because FH and FP can occur simultaneously. Excellent. All right. So we can use the same analysis. The voltmeter is equal to VA minus VB. So what's VA? Voltmeter, VA, VB. We just did this. Voltage divider, no problem. Except this time, let's look at it carefully. VA is VS times RT over RB plus RT. VB is RB over RT plus RB. Almost the same, just a switch of the T and the B. Okay, assuming no current goes through there. Okay, the voltmeter is equal to the voltage across here is this minus this voltage minus this voltage, okay, VA minus VB, so I'm just going to plug them in. And I can just collapse them because they have the same denominator, RT minus RB, good. And again, let's go through here. Remember, we got a change in R positive for increasing FP, okay? And so RT, the resistors on top are going to be whatever their nominal length was plus a delta R, yep. And the bottom ones are going to be R naught minus a delta R, yep, good. And so you can see if I only had, so this is an example, if I could perfectly not have any force here, right, and just have a force here, right? Remember our superposition, analyzing the voltmeter one force at a time, right? Or analyzing the stress and strain deflection one force at a time. So think of this as like superposition. We're ignoring this one. We're just looking at this one, okay? What's going to happen? Well, the RTs become R naught plus delta R, R naught plus delta R, and the RBs become R naught minus delta R naught minus delta R. Let's see what kind of nice simplifications happen. Well, I see minus, so this goes away. Minus, these go away. Okay, good. So I'm left with minus, that's a positive. So 2 delta R on the top and 2 R naught on the bottom. The 2's cancel. And I get the voltmeter reading is proportional to VS delta R over R naught. So what that says is as the resistance, the overall resistance in all four of these change, what happens? The voltmeter will pick it up and see that. Okay. Now let's say we went the other way. Let's say there's perfectly no force there, but we only had forces in the horizontal direction. Okay. So if that's the case, we can do the same thing. Remember, RTs, if we only have horizontal forces, you'll either get all pluses or all minuses on the delta R. Okay, so if we look here, we do the same thing. Go back to this equation. So RT minus delta R, R0 minus delta R, R0 minus delta R, R0 minus delta R, R0 minus delta R. Well, it's easy to see. This is just going to cancel, right? You get 0. That's really nice. So what this says is, even if there's forces in this horizontal direction, the voltmeter won't be able to pick it up. It'll see 0. It is insensitive. This is good. Okay, so I hope you can see that putting 4 strain gauges like so will make your system insensitive to this horizontal force and not this perpendicular force in this kind of beam bending application, right? Or a pedal. Good. All right. So we're going to write down this equation here, right? Vm equals Vs delta R over R naught. Boom, I put that there. We're going to write down our strain equation. Strain equals 1 over G delta R over R naught. Good. And we're going to put them together. Look at this. Delta R equals Vm R naught over Rs. That's what this is solved. And then I can plug it in there. So strain equals 1 over the gauge factor, R naught, right? That's R naught times this guy. R naughts cancel. So you actually don't care about the initial resistance. So the strain is equal to the voltmeter reading divided by 2. That's the gauge factor divided by the voltage source, which is like 5 volts or 3.3 volts, depending on your microcontroller. This is a constant value. This is from your voltmeter reading. This adjusts in real time. You don't have to do that silly balancing and whatever potentiometer nonsense. So the strain is directly proportional to the voltmeter reading. That is nice. Okay. Well, we still need to do this. We need to still connect strain to force to power, right? But we're nearly there because in this little tangent, what we're going to do is kind of look at our strength of materials. This hopefully is a review. I really hope this is something you've seen before or you're about to see in your classes. If you have a beam, assuming some height and some length and some cross-sectional distance, right? And you have some vertical force here, you have some neutral axis and Y, you can also find the second moment inertia of I. This hopefully is review. You can get a moment, right? A moment is like a torque. So this force times this L is the moment or torque in Newton meters on this beam, right? Or on the pedal. And we have our nice, very important stress strain equations. The stress in this beam is equal to the Young's modulus times the strain. Good. It's also equal to the moment times the distance y in the vertical direction over I. Good, right? So all these things should be familiar, I hope. Okay. And so what do we get here? What do we get? So we have the force on the pedal, right? The force on the pedal divided by, force on pedal equals this guy here, okay? Because this force pedal here is going to be equal to capital E, Young's modulus epsilon, times I, because this goes over here, right? Divided by L, because you're going to have the L in there, divided by Ym, right? Now, Ym in this case, because we're looking at the top part, is going to be whatever half of this H is, right? Because that's the stress we're looking for, okay? So this is going to be H over 2. What is this I? If you recall, if we assume a perfect rectangular cross-section, it is BH cubed over 12. That's just one of those weird things that you had to remember for your strength of materials class, BH cubed over 12. Okay, so that goes here, all right? Let me just clarify, what are all these things? E is the Young's modulus. That is a material constant, right? Okay. E is the strain. Where are we getting the strain? From the voltmeter. I, second moment inertia. L, length of the pedal. Good. Ym, H over 2, the distance from the neutral axis to where the strain gauge is. Good. Okay. By the way, for your own curiosity, if you forgot why I equals BH over cubed over 12, it does come from this. Okay. You can do this area integral, double integral here, y squared dx dy. That's the general form. So if you had some wonky cross-sectional area, you could still solve for it, right? This is just the derivation, BH cubed to get to BH cubed over 12. If you want to look at it, you can freeze the video, inspect it, make sure I did all the math correct. Hopefully I did here, and you get to BH cubed over 12, okay, units of meter to the fourth. Don't worry about this. I'm not going to test you obviously on this. Maybe the strength of materials class will, but not me. I just put it there for your curiosity. Okay, let's get back. Okay, we are nearly there. Remember, the pedal power is equal to torque times speed. Torque is force times distance. Okay, we just came up with an equation for force. It's this one, right? Okay, so it's that one there. E epsilon I over LP Ym, or H over 2. Okay, what else do we have? We have this Epsilon equals the voltmeter over GVS. Okay, so now we're punching everything in, right? We're doing some simplifications, right? What do we got here? This is BH cubed over 12. This is H over 2. What kind of simplifications can we make? H goes away with the one of the three, so that becomes a 2. The 12 and the 2 cancel to a 6. All right, so we have force is this guy here. I can take this and plug it in there, and then take this whole thing and plug it back into the force equation. And then what do I get? Okay, big Young's modulus BH squared over LP6 voltmeter GVS times LP omega. That's this LP omega. They cancel. Okay, this is good. I simplify, crunch, 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 right? And I get this. And you're like, oh my God, this is just a nasty mess of algebra. Okay, but it's not that bad if you think of it from the big picture of power is torque times angular velocity. I want to measure the torque. If I can measure the force and multiply it by the lever arm, I got the torque essentially, right? Well, how am I going to measure the force? I can use my strain gauge, right? That's a change in resistance. How do I measure the change in resistance? Wheatstone bridge. How do I get the Wheatstone bridge change in resistance? Voltmeter. Boom. So this voltmeter is representing your force. If I use the cadence meter from my, bicycle wheel, I can measure this one. And this is just a constant. So really at the end of the day, what you could do is if you actually had a real application where you wanted to design, build this and make it a product, which actually, if you look up Stages, I don't know if they're still in business, they actually sell these for like $300 to $600, something crazy. This could be a constant where you tune it later. You just get the voltmeter reading, you get the angular velocity, and you just tune this up. Pick a number, compare it against like the real power, if you're able to measure the real power, and then just kind of tweak this number until you get it right. Because all these are, this is the material constant of aluminum or whatever your pedal is. These are the geometry of your pedal. This is the voltage source of your microcontroller, right? These are all just constant numbers, right? These are the only things that will change on the fly. And so you can see if I'm not pressing with anything, this is 0, power is 0. If I'm not spinning, even if I'm pressing, right? Like if I'm pushing down, but not spinning, this is 0, power is 0, okay? If I'm pressing down and spinning, then I get non-zero power. So at the end of the day, this hopefully is not too bad, okay? All right, so then what would you do? You'd have a pedal, you'd have a battery on it, you'd have maybe a wireless transceiver to send it to your display. You'd have 4 strain gauges on your pedal. And you'd have a little gyroscope or something that's measuring the angular velocity. And you could take that and send it to either your phone or some app or something that you put on your handlebars. Well, check this out. By the way, I do have the unit conversion here. You can freeze the video and then run through all these and make sure all the units cancel out to power, right? But I'll let you do that as an exercise. What I want to show you is that in previous years, we had a student group in ET370, which is the follow-on course to 250, take this example and build a bicycle power pedal, system, which was really cool. So what do we have here? Look at the pedal. Oh my goodness, they have the strain gauges on the top and the bottom, right? They had 4, 1, 2, 3, 4, okay? And then, oh, here's the team, right? Here's their display here, and here's their pedal. And so they had a little wireless transceiver that sent to here, okay? And then this would display your power, okay? So it's pretty cool stuff. And then here's a close-up. I know it's a little rough, but you got a battery here, right? So you need to power it up. You had the strain gauges. You had a little IMU that had a gyroscope that would measure the angular velocity. And then you had an amplifier that was essentially amplifying that small little voltage signal and sending that amplified voltage signal to the little microcontroller, this is what we call an Arduino, and that was measuring the voltage. It had a wireless transceiver, so it was sending wireless data from here to here. It was a pretty involved project, and I was super impressed. But they took this project and actually built it and made it real. So pretty cool stuff. Anyways, I hope you learned something. I hope you got to see how some of the circuits and electronics can interface with real things and make some really cool technology. And these are kind of things that you'll see in your careers. An example would be the ship, the propeller. You could measure the power of the propeller by doing the same thing. You put strain gauges on the propeller on the shaft. You put some kind of sensor that measures the angular velocity, and you could measure the power at the shaft. Same idea as this pedal power meter. So I hope you liked it. But anyhow, I will see you in class. Have a good day.